If I ask you what color the universe is, you'll probably say, black. You're wrong. If we blended all the light from all the galaxies, the universe is actually a soft beige color that astronomers call cosmic latte. But that's just the tip of the iceberg. Today, we're going to travel to a planet made of ice that burns at 400 degrees without ever melting. And we'll walk on a moon where rivers, seas, and rain exist, but not of water, rather of liquid methane gas. We're going to chase an interstellar visitor shaped like a cigar that crossed our solar system and left forever, and we'll discover that Earth has a shy second moon that secretly accompanies us. Nothing you're going to see in the next 2 hours is science fiction, even though it may seem like it. There is a planet where ice burns. It sounds impossible, right? However, in the universe, logic often bends in the face of astonishing phenomena. Gliese 436b is an exoplanet located about 33 light-years from Earth, in the constellation Leo. What makes it truly extraordinary is that, despite surface temperatures exceeding 400 degrees Celsius, solid ice exists there. But how can ice remain in such a hellish environment? The key lies in extreme physics. On Gliese 436b, the atmospheric pressure is so high that water molecules stay bonded together, forming a type of ice known as Ice X. This ice does not melt even under scorching heat, because the pressure compresses it to the point of making it denser and more stable than any ice we know on Earth. It's as if you were trying to melt a cube of ice by squeezing it so tightly between your hands that, even if you put it in the fire, it simply cannot break down. Thus, on Gliese 436b, water defies the usual rules and behaves in a completely unexpected way. Can you imagine walking on a sea of ice that is literally burning? There, the surface of the planet is wrapped in an atmosphere filled with hydrogen and helium, creating a pressure cooker effect. Scientists believe that the burning ice covers the rocky core of the planet, and above it lies a layer of hot gases. It's as if this world is a cosmic pressure cooker, with its ice-resisting temperatures and conditions that would destroy any form of water on Earth. Gliese 436b reminds us that the universe is full of exceptions and wonders that surpass imagination. Not everything we call ice behaves the same way in all corners of the cosmos. Under the right conditions, even the most basic principles can be broken. Thus, on this small and distant planet, ice is not a symbol of cold, but of a strange resistance to extreme heat, challenging what we thought we knew about nature, and showing us that, in the universe, there is always room for the impossible.
If you're enjoying this journey through the universe and want to keep exploring more cosmic mysteries, don't forget to subscribe to the channel and give the video a like. Thank you for being part of this Star Odyssey.
What color is the universe? At first glance, we might think the answer is obvious. Black, like the night sky sprinkled with tiny bright dots. But the reality is much more surprising and, in fact, has a name: cosmic latte. How did astronomers arrive at this curious conclusion? It all begins with a simple yet profound question. If we mixed all the light emitted by the stars and galaxies of the cosmos, what shade would result? At the beginning of the 21st century, a team of astronomers decided to find out. They collected the light from over 200,000 galaxies, analyzing their spectra, that is, the fingerprint of the light they emit. By combining all those colors, from the reddish hues of the oldest galaxies to the bluish tones of the youngest, they discovered that if that light could be concentrated into a single point, the resulting color would be a very soft, almost creamy beige. They named it cosmic latte, as if the entire universe were a gigantic cup of coffee with milk. Why isn't it blue, white, or even red? The answer lies in the history of the cosmos itself. Young galaxies tend to emit bluer light, but over billions of years, stars age and the reddish and yellowish tones dominate. The mixture of all these colors, weighted by the number of stars and their life stage, results in that peculiar hue. Thus, cosmic latte becomes a kind of average color of all the visible light that exists in the universe. This finding reminds us that even seemingly simple concepts can have unexpected answers. The color of the universe speaks to us about its age, the evolution of stars, and the processes that have occurred since the Big Bang. It's not just a curiosity, it's a clue about the history and destiny of everything that exists. So, the next time you look up at the sky and see the darkness, think that if you could gather all the light of the cosmos into a single beam, you would see a color as soft and subtle as cosmic latte, the true hue of the universe. In the vast catalogue of cosmic wonders, few are as intriguing and puzzling as Hoag's object. What makes this galaxy so special? At first glance, it appears to be an almost perfect ring of blue stars surrounding a spherical core, as if the universe had drawn a gigantic eye in space. But how could such an orderly structure, yet so uncommon, have formed? Astronomers have been trying to decipher this enigma for decades, and to this day, Hoag's object continues to challenge conventional explanations of galactic formation. Most ring galaxies are created from violent cosmic collisions, when one galaxy passes through the heart of another, generating shock waves that push gas and stars outward, forming the characteristic ring. However, in the case of Hoag's object, no clear evidence of an intruding galaxy or gravitational scars has been detected to explain its peculiar shape. Could this be a unique case in the universe, an exception to the known rules? The almost perfect symmetry of the ring and the apparent tranquility of its core raise fascinating questions about the processes that can sculpt such delicate structures on such gigantic scales. The ring itself is composed of young, hot stars that shine with a bluish hue, while the core is a sphere of much older, reddish stars. This difference in age and color of the stellar populations suggests that the ring and the core had separate evolutionary histories before merging into their current state. Is it possible then that the ring formed from the accumulation of external gas, or perhaps through interaction with an invisible galaxy composed almost entirely of dark matter? So far, no hypothesis has fully convinced the scientific community. Hoag's object is a reminder that even among trillions of galaxies, there is always room for the unexpected. Its existence invites us to think that the universe still holds secrets to be discovered, and that cosmic laws can produce wonders that defy our intuition. Every time astronomers observe this cosmic ring, they face the same question. What other unsuspected forms might the cosmos take? And above all, are we prepared to find answers that rewrite what we think we know about the nature of the universe? What object in the universe can spin hundreds of times per second and still maintain the precision of an atomic clock? The answer is pulsars, the true cosmic clocks. Pulsars are extremely dense neutron stars, born from the violent death of stars much larger than our Sun. When a massive star explodes in a supernova, its core collapses under gravity and compresses to such an extent that protons and electrons fuse into neutrons, forming a sphere about the size of a city, but with a mass greater than that of the Sun. But how does this cosmic clock work? The key lies in the dizzying rotation and powerful magnetic fields of pulsars. These objects spin at incredible speeds. Some complete a rotation in a fraction of a second. Imagine a figure skater spinning faster and faster by pulling in their arms. Something similar happens to the neutron star when it collapses, conserving the angular momentum of the original star, but multiplying its spin rate as its size decreases. As they spin, they emit beams of electromagnetic radiation from their magnetic poles. If the orientation is just right, these beams sweep through space, and from Earth, we detect them as regular pulses of light, like the rhythmic flash of a cosmic lighthouse. The regularity of these pulses is so astonishing that many scientists, when they were first discovered in 1967, thought they could be signals of intelligent life. In fact, pulsars compete with the best atomic clocks on Earth in terms of precision. Some, like the famous Crab pulsar, pulse with such accuracy that they have been used to measure cosmic distances, track gravitational waves, or even test Einstein's general theory of relativity under extreme conditions? Can something so small and dense really challenge our notion of time? The answer is yes. Pulsars slow their rotation very slowly, losing energy with each pulse, yet they still maintain an impressive regularity for millions of years. Thanks to them, astronomers have managed to create a kind of network of natural clocks scattered throughout the galaxy, allowing the study of exotic phenomena such as binary neutron star systems, and even searching for tiny variations in the very fabric of space-time. In the universe, when it comes to measuring the passage of time, no mechanism is as precise and fascinating as a pulsar. What would you do if a star flickered unpredictably in the sky, as if trying to send a message in code? Such is the enigma surrounding Tabby's star, officially known as KIC 8462852. Located in the constellation Cygnus, this star has puzzled astronomers with its strange behavior. Its brightness decreases irregularly, sometimes losing up to a fifth of its total luminosity before shining normally again. What could be causing these peculiar and abrupt dimmings? In most stars, brightness variations usually have simple explanations: planets passing in front, stellar spots, or clouds of dust. However, Tabby's star defies all these conventional explanations. Planetary transits, for example, produce regular and predictable decreases in the star's light, but Tabby's dips are chaotic, with no apparent pattern and varying depths. Imagine a light bulb that, instead of flickering in a rhythm, does so completely anarchically, sometimes dimming briefly, and other times darkening for several days. Faced with this mystery, the creativity of the scientific community soared. One of the first theories suggested the presence of a cloud of giant comets or debris fragments, remnants of some disintegrated celestial body passing between the star and us. But can a cloud of comets really explain such intense and prolonged dimmings? Simulations show that a gigantic swarm, extremely rare, would be needed to cause such fluctuations. And moreover, the expected dust signatures have not been detected in this type of scenario. The lack of a clear explanation led some to propose even bolder hypotheses. What if some artificial megastructure were blocking the star's light? The idea of a Dyson sphere, a hypothetical construction created by an advanced civilization to capture stellar energy, captured the public's and some scientists' imagination. However, observations at different wavelengths, including infrared, do not show the excess heat one would expect from such a structure. For now, the most likely explanation still points to extremely fine and opaque dust clouds, perhaps expelled by the star itself or by still unknown nearby bodies. Despite years of study, Tabby's star remains one of the most intriguing objects in the cosmos. Every time its brightness fluctuates again, it reminds us of how much we still do not know about the universe and how easy it is to underestimate the complexity of nature. Are we facing a completely new phenomenon, or have we simply not yet asked the right question? The mystery remains open, inviting future generations of astronomers to seek answers in the flickering light of a distant star. In October 2017, astronomers detected something they had never seen before: a strange object traversing the solar system at an impressive speed and on a trajectory that did not match that of known comets or asteroids. What was this interstellar rock coming from another part of the galaxy? Its name is Oumuamua, which in Hawaiian means the messenger that arrives first from afar. But why did its discovery cause such a stir? The first thing that puzzled scientists was its hyperbolic orbit. While objects in the solar system move in elliptical paths, Oumuamua was traveling so fast that even the sun could not hold it. It came from outside and would continue its journey into infinity. What material was this visitor made of? Here another surprise arises. Unlike comets, Oumuamua did not leave a trail of dust and gas as it approached the sun, but it did not behave like a simple rocky asteroid either. Its surface appeared very reflective, almost metallic, and it spun chaotically, like a bottle thrown into the air. One of the most intriguing features was its shape. Can you imagine a cosmic cigar, or perhaps a kind of elongated loaf floating among the stars? Calculations suggest that Oumuamua was up to 10 times longer than it was wide, something totally unusual for the natural bodies we know. How could such a structure form? No one knows for sure. Some scientists propose that it could be a fragment detached from a destroyed planet, while others even imagined alien technologies. But so far, the explanation remains an open mystery. Where did Oumuamua come from? Analyzing its trajectory, it seems that it traveled for millions of years from another star, crossing the interstellar void before briefly passing through our neighborhood. And just as it arrived, it left. In just a few weeks, it was already too distant and faint to be observed. Its brief visit reminded us of how little we know about the objects that wander among the stars, and how vast and unpredictable the universe is. How many messengers like Oumuamua are crossing space right now without us even realizing it? Can there be snow in space? The answer is yes, but not like the snow we know on Earth. In the solar system, there is a world that produces its own snow of water, Enceladus, one of Saturn's moons. This small satellite, covered by a bright and icy surface, hides vast oceans of liquid water beneath its crust. But the most surprising thing is not just the existence of water, but the way Enceladus releases it into the cosmos through gigantic geysers that expel particles of ice and vapor from its south pole. What makes these geysers special? Imagine a pressure cooker trying to release energy. The internal heat of Enceladus, generated by Saturn's gravitational stretching, melts part of the ice beneath the surface and creates enormous pockets of liquid water. When the pressure is sufficient, that water escapes violently through fractures known as tiger stripes, forming columns that can reach hundreds of kilometers in height. As it exits into the frigid space, the water freezes almost instantly, creating a kind of permanent snowfall that, over time, helps feed Saturn's E-ring. But why does this fascinate scientists so much? Because the material expelled by the geysers is not just ice. It contains salts, organic compounds, and even particles that could indicate complex chemical reactions. In other words, Enceladus is not just a factory of space snow, but it could also hide the basic ingredients for life. Space missions like Cassini have passed through these plumes and analyzed their composition, revealing secrets that have revolutionized our search for life beyond Earth. Could there be life beneath Enceladus's icy surface? Although there is still no definitive proof, the presence of liquid water, energy sources, and complex molecules makes this world one of the most promising places to search for life in the solar system. Thus, Enceladus and its geysers remind us that even in the coldest and most distant places, the universe holds surprises capable of challenging our imagination. Did you know that there are places in space where the gravity of two bodies, like the Earth and the Sun, balances so precisely that an object can float there almost without moving? These sites are known as Lagrange points, and they are true cosmic parking spots. But how is it possible that in the vast emptiness of space, there are such perfect equilibrium zones? The explanation lies in the gravitational dance between celestial bodies. In every system of two massive objects, like a planet and its star, 5 specific points are formed where gravitational forces and inertia cancel each other out. It's as if in a constantly moving slide, there were invisible platforms where you could stand without sliding in any direction. Lagrange points are not only a fascinating concept, but they have revolutionized space exploration. Why? Because in these places, a spacecraft or satellite needs to expend very little energy to maintain its position. For example, Lagrange Point 2, located beyond the Earth in the opposite direction of the Sun, is the favorite destination for space telescopes like the James Webb. From there, they can observe the universe without being disturbed by the Earth's glare, while simultaneously maintaining a stable position with minimal fuel. Have you ever wondered what happens if an object is placed at one of the other Lagrange points? 2 of them, Lagrange 4 and Lagrange 5, form a perfect triangle with the Earth and the Sun. They are considered especially stable, as if they were the corners of an invisible triangle where asteroids, known as Trojans, can be trapped for millions of years. In contrast, points 1, 2, and 3 are less stable, and objects placed there can easily drift if given a slight push, like leaves floating on water. These equilibrium points are not only useful for science and technology, but they also show us the delicate balance that reigns in the cosmos. They allow scientific missions to be positioned in privileged spots to observe deep space, study the sun, or monitor space weather. Thus, Lagrange points function as true cosmic parking spots, reminding us that even in the apparent chaos of the universe, there are islands of stability calculated with almost unimaginable precision. What would you send into space if you had the chance to leave a message for unknown civilizations? In 1977, humanity attempted to answer that question by launching 2 space probes, Voyager 1 and Voyager 2, each equipped with a golden record. But why a record, and what exactly does this interstellar message contain? The golden records of the Voyagers function as a time capsule, a cosmic greeting for any intelligent life that, perhaps millions of years from now, might encounter one of these wandering ships. These records are not just simple vinyl discs. They are gold-plated plates designed to withstand the passage of time and the hostilities of interstellar space. And what is recorded on them? A carefully curated selection of sounds, images, and greetings in 55 languages. From the cry of a newborn to the songs of whales, including welcome greetings in languages from around the world, and universal musical pieces like Beethoven's Fifth Symphony, or traditional songs from various cultures. Scientific diagrams and data about Earth's location in the universe are also included, as if humanity had left a map saying, "Here we are." Why send such varied data? The idea was to showcase the diversity and richness of human life and culture. It's like throwing a bottle into the cosmic ocean, hoping that if someone ever finds it, they can decipher who we were and what our home was like. Could an extraterrestrial civilization understand our music or our drawings? Although the probability is infinitesimally small, the attempt is a statement of curiosity and hope. The records even include a guide so that, regardless of the language or biology of the receiver, the content can be interpreted. Everything was thought out down to the last detail, from the rotation speed of the record to the way to read the encoded images. Does it make sense to send a message that perhaps no one will ever hear? For many scientists, the answer is yes. The golden records of the Voyagers are, in part, an act of faith in the possibility that we are not alone and in the capacity of human knowledge to transcend the boundaries of time and space. Although they are likely to drift silently through the interstellar darkness, they represent one of the most poetic and ambitious feats of our species. The desire to connect, to be understood, and ultimately, to leave a mark in the vast ocean of the cosmos. How big can a star be? When we think of giants in space, it's easy to imagine enormous bodies, but Stephenson 218 redefines the concept of stellar gigantism. It is a red hypergiant, classified as the largest known star to date. To get an idea of its size, if we were to replace the Sun with Stephenson 218, its surface would exceed the orbit of Saturn. We are talking about a star with a radius over 2,100 times that of the Sun, a true cosmic colossus. How is it possible for a star to reach such proportions? The answer lies in its evolutionary stage. Stephenson 218 is a star that has exhausted the hydrogen in its core and is now fusing heavier elements, causing its outer layers to expand enormously. In this process, the density of the star decreases so much that, although its size is immense, its matter is distributed in a gigantic volume, and its atmosphere is extremely tenuous. It's like trying to inflate a balloon to the size of a stadium. Most of it would be empty space. And what implications does discovering such a colossal star have? Its existence challenges current models of stellar evolution because it raises questions about how such massive stars form and how long they can last before collapsing. It is estimated that Stephenson 218 has a short life in astronomical terms, just a few million years, a minimal fraction compared to the longevity of stars like our Sun. Moreover, it will eventually end its life spectacularly, probably in a supernova explosion capable of seeding space with heavy elements. Could there be even larger stars waiting to be discovered? It's possible. The universe is so vast and enigmatic that there is always the possibility of finding new extremes. For now, Stevenson 218 holds the title of the absolute giant, reminding us that in the cosmos, records are always meant to be broken. Thus, each discovery expands the limits of our understanding and invites us to continue exploring the mysteries of the sky. In the depths of the observable universe, there exists an anomaly that has intrigued scientists for years: the cold spot of the cosmic microwave background radiation. But what exactly is this spot, and why does it challenge our understanding of the cosmos? To understand it, we must first travel to the oldest echo of the universe, the cosmic microwave background radiation, that faint glow left after the Big Bang that fills all of space like a kind of thermal backdrop. This radiation should be, in theory, almost perfectly uniform, with tiny fluctuations corresponding to the seeds of future galaxies. However, among those small variations, there is an unusually colder and larger region than the rest, the famous cold spot. Why is this area so special? The cold spot is not only colder than average, but it is also broader than any standard cosmology model would predict. If we compared the cosmic background radiation to the surface of a calm lake at dawn, the cold spot would be like finding, in the middle of the lake, a zone of water that is noticeably colder and deeper without any apparent reason. Scientists have measured that this region spans hundreds of millions of light years and has a temperature about 70 microkelvins lower than the average. It may seem small, but on cosmic scales, this difference is truly significant. Explanations for this phenomenon have been varied and, in many cases, surprising. One of the most popular theories suggests that the cold spot could be due to a supervoid, that is, a gigantic region of space that is practically empty, with fewer galaxies and matter than average. While large voids have been detected near the direction of the cold spot, none seem large enough to fully explain the anomaly. Then the question arises, what if the cold spot is the footprint of something even stranger, like a collision between our universe and another bubble universe in a larger multiverse? This hypothesis, while fascinating, remains highly speculative and lacks direct evidence. Despite decades of observations and analysis, the cold spot remains one of the great cosmological enigmas. Is it simply a statistical whim, an improbable but possible fluctuation within known laws? Or is it the gateway to new physics that we do not yet understand? The mystery remains open, and for now, the cold spot reminds us how little we truly know about the universe and how many secrets are still waiting to be discovered in that vast cosmic ocean. What if I told you that, in the solar system, there is a world where it rains, but not water, rather liquid methane? Titan, Saturn's largest moon, is one of the strangest and most fascinating places we know. Its atmosphere is so dense that it resembles a planet, and its surface is marked by rivers, lakes, and seas, but formed by organic compounds like methane and ethane. How is it possible for such a cold body to have lakes and seas? The key lies in its extreme temperatures, which hover around 180 degrees below zero, allowing methane and ethane to exist in liquid form, just like water on Earth. Titan is the only other world in the solar system, besides our planet, where the existence of stable liquid bodies on the surface has been confirmed. These methane lakes and seas not only cover vast regions, but also participate in a cycle similar to the Earth's water cycle. There is evaporation, cloud formation, precipitation, and surface runoff. Can you imagine a hydrological cycle, but with methane? On Titan, the landscapes are sculpted by hydrocarbon rains, generating deltas and channels that could be mistaken for Earth's rivers if it weren't for their exotic composition. But how big are these lakes? Some, like Kraken Mare, surpass the Caspian Sea in size. Their shores and coasts are made up of a mix of water ice and solid organic compounds, creating an alien and astonishing geography. The Cassini probe, along with the Huygens lander, allowed us to peek into this world and discover that there are even waves and possibly mists over the surface of these lakes. Could there be life in such an extreme environment? Scientists speculate that, although it would be very different from the life we know, certain forms could adapt to methane solvents, opening the door to a completely new biology. Despite its remoteness and opaque atmosphere, Titan continues to spark humanity's curiosity. Its nitrogen-rich atmosphere and complex chemistry make it a natural laboratory for studying how the precursor processes of life might have begun on primitive Earth. Titan challenges us to imagine impossible forms of life and landscapes, reminding us that, in the universe, the diversity of worlds far exceeds our imagination. Did you know that Earth is not alone on its journey around the Sun? While we all know the Moon as our only natural satellite, there is a small cosmic companion that has gone unnoticed for centuries, Kamo'olawa. Its name, of Hawaiian origin, means oscillating fragment, and this mysterious object moves in a strange dance around our planet, always staying close but not being a traditional moon. How is it possible that we have a second moon without most people knowing? The key lies in its unique and discrete orbit. Kamo'olawa is an asteroid just a few dozen meters in diameter, but its significance goes far beyond its size. It orbits the Sun almost at the same rate as Earth, but in a path that makes it appear as if it is circling us, accompanying us on our annual journey. This behavior makes it what astronomers call a quasi-satellite. Unlike the Moon, which is gravitationally bound to Earth, Kamo'olawa follows a trajectory that keeps it close, but it is the Sun that truly dominates it. It's like a runner who stays close to another on the track, always near but not holding hands. Where does this mysterious object come from? Scientists are still debating its origin. One fascinating hypothesis suggests that it could be a fragment that broke off from the Moon itself during an ancient impact, making Kamo'olawa not just a neighbor, but a lost brother. Its spectral characteristics, which reflect light similarly to lunar rocks, reinforce this theory, although there is no definitive consensus. Are we sharing our cosmic path with a piece of our most distant history? Despite its relative proximity, detecting Kamo'olawa is not an easy task. Its small size and faint brightness make it an orbital ghost, invisible to the human eye and only observable with powerful telescopes. However, the scientific interest is enormous. Studying Kamo'olawa can help us better understand the dynamics of near-Earth objects and the violent past of our planetary system. Thus, the second moon reminds us that the universe always holds secrets, even in the most familiar neighborhoods. How many other unknown companions are traveling alongside us in the darkness of space? How big can a structure in this universe be? If we think about galaxies and clusters of galaxies, we are already talking about astonishing dimensions. But there is something that surpasses all imagination: the Hercules Corona Borealis Great Wall. This colossal structure is so vast that it would take light nearly 10 billion years to cross it from one end to the other. Yes, that's almost as long as the age of the known universe itself. How is it possible for something so gigantic to exist? The Great Wall is not a physical wall like those we know on Earth, but a massive grouping of galaxies, clusters, and superclusters that form a kind of cosmic filament. Imagine it as if the universe were a three-dimensional spider web, and the Great Wall were one of those particularly thick and extensive threads. Its discovery in 2013 shook the scientific community because it challenges theories about how matter should be distributed on the largest scales. What is this wall made of? It is composed of thousands of galaxies, each with hundreds of billions of stars. But the most astonishing thing is that, according to the current cosmological model, there shouldn't be structures this large. The existence of the Great Wall tests the homogeneity of the universe, the idea that, if we look on a large scale, the cosmos is more or less the same everywhere. However, this structure seems to go against that notion, as if the universe had gigantic scars that we still cannot fully explain. What does this finding imply for our understanding of the cosmos? On one hand, it forces us to rethink certain aspects of galaxy formation and the evolution of the universe. Could there be even larger structures? Or does the Great Wall represent a natural limit? These questions remain open. In the meantime, the Hercules Corona Borealis Great Wall stands as one of the most impressive enigmas, reminding us that no matter how much we think we know, the universe always has something even vaster and more surprising waiting for us. In the heart of the constellation Scorpius, over 3,000 light-years away, lies one of the most impressive and enigmatic structures in the cosmos, the planetary nebula NGC 6302, popularly known as the Butterfly Nebula. How is it possible that the death of a star gives rise to one of the most beautiful forms in the universe? At first glance, it appears to be a cosmic butterfly spreading its wings of gas and dust. But in reality, we are witnessing the final act of a star similar to the Sun, which, after exhausting its fuel, violently expels its outer layers into space. What physical processes create those luminous and symmetrical wings? The key lies in the interaction of extremely fast stellar winds, which collide with previously expelled slower material. This collision generates temperatures of over 200,000 degrees and sculpts the matter into astonishing shapes. The ultraviolet radiation from the central star, now turned into a white dwarf, ionizes the surrounding gas, causing it to glow in colors ranging from blue to deep red, depending on the elements present. It's as if the star, in its death, paints one last brilliant picture before slowly fading away. Why does this nebula have such spectacularly symmetrical shape? Although it seems like a deliberate work of art, astronomers believe that the symmetry of the Butterfly Nebula may be due to the presence of a companion star, or even a disk of material around the central star, which channels the gas ejection in opposite directions. This phenomenon is not exclusive to NGC 6302, but here the perfection of natural design is especially striking. The distance between the tips of its wings exceeds a light-year, equivalent to nearly 10 trillion kilometers. What does the Butterfly Nebula teach us about the fate of our own Sun? In about 5 billion years, our star could meet a similar end, expanding and forming its own planetary nebula. These stellar remnants are not only beautiful, but they are also fundamental to cosmic recycling. The heavy elements released in these events are incorporated into new generations of stars and planets. Thus, the cycle of life and death of stars continues, and each cosmic butterfly is a silent witness that beauty can arise even at the end of a stellar existence. Did you know that our galaxy, the Milky Way, is destined to star in a colossal encounter with its closest neighbor, the Andromeda Galaxy? Although both appear calm and distant in the night sky, they are actually traveling towards each other at a speed of about 400 kilometers per second. But what happens when two galaxies, each with hundreds of billions of stars, come face to face in the void of the cosmos? This event, known as a galactic collision, can be compared to a cosmic waltz. Two giants slowly spinning until they intertwine and merge their destinies. Contrary to what we might imagine, the collision will not be a chaotic explosion where stars destroy each other. In fact, the space between stars is so vast that the probability of direct collisions is minimal. It is more likely that the stars will simply change positions, as if millions of fireflies were dancing in a huge hall without touching each other. However, gravitational forces will indeed cause significant changes. The spiral arms of both galaxies will distort, enormous clouds of gas will compress, and new waves of star formation will ignite, lighting up the sky like cosmic fireworks. When will this great encounter happen? Approximately in 4 billion years, a span that is unimaginable on a human scale, but just a moment for the universe. In that distant future, the Milky Way and Andromeda will merge into a single giant galaxy, which some astronomers are already calling lactomed. Will our solar system disappear in the process? It is unlikely, but the position of the Sun within the new galaxy could change radically, pushing us to a more distant corner or bringing us closer to the galactic core. This galactic waltz is not an isolated case. Collisions and mergers of galaxies are common in the history of the universe and are key to understanding its evolution. In fact, it is believed that many large galaxies, like ours, are the result of multiple mergers over billions of years. Thus, while we contemplate the sky and see the diffuse silhouette of Andromeda, we are actually witnessing the prelude to a grand cosmic spectacle that will forever transform the galactic neighborhood. Isn't it amazing to think that our own stellar home is part of such a majestic and eternal dance? Have you ever wondered what the final fate of the universe will be? Beyond the death of stars and the cooling of galaxies, scientists have proposed a fascinating and little-known hypothesis, the era of iron stars. What are these mysterious stars and why do they represent the last gasp of activity in the cosmos? To understand this, let's first think about the life cycle of stars. Today, most stars shine thanks to nuclear fusion, transforming hydrogen into helium and, in more advanced stages, fusing heavier elements like carbon and oxygen. But fusion has a limit: iron. When a massive star produces iron in its core, the energy required to fuse this element is greater than what is gained, causing the star to collapse and often end its life in a supernova explosion. However, in an unimaginably distant future, when the formation of new stars has ceased and the reserves of hydrogen are depleted, only the stellar remnants will remain: white dwarfs, neutron stars, and black holes. This is where the hypothesis of iron stars comes into play. Over trillions of years, white dwarfs, those cooled stellar cores, could undergo a process called quantum decay, in which protons disintegrate and lighter elements slowly transform into iron, the most stable element in the universe. Can you imagine a cosmos filled with cold, dark spheres made almost entirely of iron? But what does this mean for the universe? Iron stars would be like the ultimate fossils of the cosmos, unable to shine, devoid of energy, silent witnesses to a frozen eternity. Their formation is so slow that it far exceeds the current age of the universe. We are talking about timescales so long that they challenge our understanding, surpassing even the usual concepts of millions or billions of years. When all forms of energy have dissipated, when even black holes have evaporated their mass through Hawking radiation, iron stars could be all that remains, silent monuments to a luminous past. Thus, the era of iron stars is a chilling vision of the ultimate fate of the universe, where even darkness does not shine and time seems to lose its meaning. It reminds us that, although the cosmos may seem eternal and active now, everything evolves towards absolute stillness, and that the current wonders are just a moment in the vast cosmic history. Will this be the true end, or are there still mysteries to uncover in the depths of time? What happened in the universe before the first stars existed? This is one of those questions that transports us to a mysterious and little-known time, the so-called Dark Age of the Cosmos. After the Big Bang, around 13,800 million years ago, the universe was a hot and dense soup of elementary particles. But after a few 100,000 years, the temperature dropped enough for protons and electrons to combine and form hydrogen atoms. This was the moment when the universe became transparent, allowing light to travel freely. However, that light was so weak and diffuse that, in practice, the cosmos remained shrouded in deep darkness. For millions of years, there wasn't a single star lit. The universe was like a vast black ocean, full of hydrogen and helium, but without any point of light. How do we know that this period of absolute twilight existed? Thanks to the cosmic microwave background radiation, that faint thermal imprint of the Big Bang that we can still detect today. But beyond that glow, the Dark Age is like a blank page. no telescope can directly observe what was happening back then. What was happening in those cosmic shadows? Although there were no stars, gravity was quietly doing its work. In certain regions, matter began to cluster into increasingly dense clouds. It's as if, in the midst of an endless night, invisible drops of water were gathering in the atmosphere, preparing to form the first rains. These gas clouds would eventually reach the mass and density necessary to ignite nuclear fusion and give rise to the first generation of stars, known as population 3 stars. Why is it so important to understand the Dark Age? Because in that primordial silence, the conditions for everything that came after were forged. The stars, the galaxies, and ultimately, ourselves. Astronomers search for traces of this era by observing the so-called 21-centimeter line, a radio signal emitted by neutral hydrogen that could reveal what that universe was really like before the light. Thus, the Dark Age is not just a chapter in the history of the cosmos, but the gateway to the birth of light and the complexity that today marvels humanity. How do you photograph something that, by definition, does not let light escape? That was the question that intrigued scientists around the world for decades. Black holes, those cosmic monsters that devour matter and energy, seemed doomed to visual anonymity. However, in the year 2019, humanity achieved the unthinkable, capturing the silhouette of one of these enigmas, located at the heart of galaxy M87, over 50 million light-years away. How was this historic achievement possible? The key lies in understanding that, although we cannot see the black hole itself, we can observe the extreme effects it causes around it. In the immediate environment of the event horizon, matter is accelerated to speeds close to that of light, heating up to shine intensely. It's as if an invisible monster is cloaked in a halo of bright fire, leaving a central shadow, the silhouette of the black hole. To capture that image, it was necessary to create a telescope the size of planet Earth. Using a network of radio telescopes distributed around the world, this technique, called Very Long Baseline Interferometry, allowed the data from each observatory to be combined and achieve an unprecedented resolution. Have you ever wondered why the image we obtained looks like a blurry ring and not a perfect circle? The answer lies in Einstein's general relativity. The immense gravity of the black hole curves space-time and distorts the path of light, causing rays that pass close to it to bend and swirl before escaping. Thus, what we see is a kind of shadow surrounded by a luminous ring whose shape and size match the theoretical predictions made over 100 years ago. This achievement not only confirmed the existence of black holes as described by the equations, but also opened a new window to study the limits of the universe and of physics itself. Now, scientists can analyze the behavior of matter under extreme conditions and test fundamental theories. Photographing the shadow of the monster was much more than obtaining an image. It was peering, for the first time, into the abyss where known laws begin to fade. What other secrets await to be captured in the darkness of the cosmos? Did you know that there are planets that travel completely alone through the galaxy, far from the light and heat of any star? These mysterious worlds are known as rogue planets or interstellar planets. They do not orbit any sun. Instead, they float freely in space, shrouded in almost total darkness. For a long time, astronomers thought that all planets must be tied to a star. But the universe, once again, defies our expectations. How is it possible for a planet to end up alone, without a sun to accompany it? The most accepted explanation is that these planets were born near a star, like Earth, but at some point were expelled from their system due to violent gravitational interactions. Imagine the chaos of a cosmic billiards game, where giant planets and newly formed stars push and launch smaller bodies into the void. Another possibility is that some rogue planets form directly from clouds of gas and dust, as if they were stars that never acquired enough mass to shine. How many of these solitary worlds exist? Estimates vary, but some studies suggest there could be more rogue planets than stars in the Milky Way. That means that for every point of light you see in the sky, there are multiple planets wandering in the darkness, invisible to the naked eye. Detecting them is not easy, as they do not emit their own light and only reveal their presence when, by chance, they pass in front of a distant star and their gravity acts like a magnifying glass, briefly distorting the light. This is the phenomenon known as gravitational microlensing. Could there be life on a rogue planet? Although it seems unlikely at first glance, some scientists believe it is possible. If a planet has a hot core and thick layers of ice, it could maintain warm underground oceans, protected from the extreme cold of space. In that environment, life could find refuge, feeding off internal energy sources. Thus, even in the most inhospitable and lonely places in the universe, nature could surprise us once again, demonstrating that life is much more resilient and adaptable than we imagine. Can the universe produce sound? Although space is a vacuum where traditional sound waves cannot travel, there is a way in which the cosmos can indeed vibrate through gravitational waves. These waves are disturbances in the fabric of space-time, generated by cosmic events as extreme as the merger of black holes or neutron stars. But how do we detect something we cannot see or hear directly? The answer lies in precision engineering and scientific patience. Gravitational waves were predicted by Albert Einstein over a century ago, but for decades they were considered impossible to measure. Everything changed in 2015 when the LIGO Observatory first detected the passage of one of these waves. What does this mean in simple terms? Imagine throwing a stone into a pond. The waves spread across the surface, except in this case, the surface is space-time itself, and the stones are cosmic collisions of massive objects. These waves carry information about the most violent and energetic events in the universe, which would otherwise be invisible to our traditional telescopes. The most fascinating part is that the signals captured by the detectors can be transformed into audible sounds for humans. Thus, scientists have managed to literally hear the universe. Chirps and hums that narrate the deadly dance of black holes and neutron stars spinning and merging at unimaginable speeds. Each gravitational wave reveals details about the mass, distance, and nature of these objects, allowing us to reconstruct stories that happened millions or even billions of light years away. What is the purpose of listening to the cosmos? Beyond the wonder, these observations have opened a new window to the universe. Thanks to gravitational waves, it is possible to study phenomena that do not emit light, such as black holes, and to test fundamental theories of physics. As the sensitivity of the detectors improves, even more hidden secrets in the depths of space are expected to be discovered. The universe, silent to our ears, has much to tell if we learn to listen to its deepest vibrations. Did you know that auroras, those light shows that paint the night sky of Earth, are not exclusive to our planet? Auroras are the result of charged particles from the solar wind colliding with the atmosphere and exciting the gases, producing flashes of colors. But what happens when we take this phenomenon to other worlds in the solar system? How do auroras look on giant planets like Jupiter or Saturn? And what secrets do they reveal about their atmospheres and magnetic fields? On Jupiter, the gas giant, the auroras are colossal and much more powerful than those on Earth. Unlike our planet, where green dominates due to atmospheric oxygen, on Jupiter, the auroras primarily shine in ultraviolet and extend thousands of kilometers around the poles. This is due to its incredibly strong magnetic field, the strongest of all the planets in the solar system. Additionally, the volcanic moon Io plays a crucial role. Its eruptions launch enormous amounts of material that, when interacting with Jupiter's magnetic field, intensify the auroras. It's almost as if Jupiter has an extra source of cosmic fireworks, fueled by its own moon. On Saturn, the auroras are also impressive, though different from those on Earth. Instead of a single predominant color, they can glow in blues and violets, depending on the composition of the atmosphere and the intensity of the solar wind. Both on Jupiter and Saturn, auroras are not only seen at the poles, but can appear in other regions due to the complex interactions between the solar wind and their enormous magnetic fields. This phenomenon is so energetic that if our eyes were sensitive to ultraviolet light, we would see the skies of these planets covered in luminous curtains almost all the time. What about even more distant or exotic worlds? Auroras have also been detected on Uranus and Neptune, although they are much less studied. Their magnetic fields are tilted and offset from their rotation axes, creating unpredictable auroral patterns. Even some moons, like Ganymede, the largest of Jupiter, may have their own auroras thanks to their independent magnetic fields. Imagining a night sky on Ganymede covered in mysterious lights is a reminder that the natural phenomena that amaze us on Earth can take unexpected forms in other corners of the cosmos. Ultimately, auroras on other worlds are much more than just a visual spectacle. They are windows into the physics of the planets, the strength of their magnetic fields, and the composition of their atmospheres. Observing and understanding them helps us decipher how these worlds function and what their conditions might be for harboring life. Will we ever witness, with our own eyes, an aurora dancing over the skies of another planet? The universe undoubtedly still holds many luminous spectacles waiting to be discovered. Is it possible that space, that vast stage between planets and galaxies, is not really empty? For centuries, scientists imagined the vacuum as an absolute nothingness, a place without matter, without energy, without anything. However, quantum physics revolutionized this idea and showed us that the vacuum is much more mysterious and active than it seems. Even the loneliest, darkest corner of the universe is infused with incessant activity, invisible to the naked eye. At the heart of the quantum vacuum, particles and antiparticles spontaneously arise and annihilate in infinitesimal fractions of a second. It's as if the universe is playing coin toss, creating pairs of particles that appear and disappear before we can notice them. This phenomenon, known as quantum fluctuations, occurs everywhere, even in the seemingly most desolate space. How is it possible for something to arise from nothing, even if only for a moment? The answer lies in the fundamental principles of quantum mechanics, which allow the energy of the vacuum to fluctuate and briefly manifest as matter. But do these fluctuations have real effects? Surprisingly, yes. One example is the so-called Casimir effect. If we place two metallic plates extremely close together in a vacuum, the pressure created by virtual particles causes them to attract each other. It's as if the vacuum itself is pushing objects, revealing that empty space is far from inert. This effect has been experimentally measured, demonstrating that the quantum vacuum has tangible physical properties. The quantum vacuum also plays a crucial role in the fate of the universe. It is believed that the so-called dark energy, responsible for the acceleration of cosmic expansion, could be related to the energy contained in the vacuum. Thus, what seems like absolute nothingness is, in reality, an invisible sea of energy and possibilities. The quantum vacuum reminds us that, in the universe, even the deepest silence is filled with secrets yet to be discovered. What do Jupiter and Saturn have in common, besides being the largest planets in the solar system? Both are gas giants, true colossi primarily composed of hydrogen and helium, so massive that together they account for more than 90% of all the planetary mass orbiting the Sun. But what does it really mean to be a gas giant? Unlike Earth, they lack a solid surface on which one could land. If you tried to descend through their atmosphere, you would simply sink deeper into layers of gas, facing pressures and temperatures impossible for any Earth spacecraft. Jupiter, the king of planets, is so large that over 1,300 Earths could fit inside it. Its atmosphere is marked by bands of multicolored clouds and the famous Great Red Spot, a storm so vast that it could engulf our planet several times over. This giant has an extraordinarily strong magnetic field, much greater than that of Earth, capable of trapping particles and creating gigantic auroras at its poles. Moreover, its gravity is so intense that it acts as a natural shield for the inner planets, deflecting or capturing asteroids and comets that could threaten Earth. And what about Saturn? Universally known for its stunning rings, this planet is a unique spectacle in the solar system. But did you know that these rings are primarily made up of tiny particles of ice and rock, some as small as grains of dust and others the size of mountains? Saturn's rings are so extensive that if we could place them around Earth, they would cover the sky from horizon to horizon. However, despite their majesty, the rings are fragile and could disappear in just a few million years, a mere breath in the scale of cosmic time. Both planets possess a multitude of moons, each with fascinating characteristics. Jupiter has over 80 moons, including Europa, which may hide an ocean beneath its icy surface, and Ganymede, the largest moon in the solar system. Saturn is also home to true frozen worlds, like Titan, with lakes of methane and a dense atmosphere. What do these giants teach us? That the solar system is far from a boring or predictable place. Rather, it is a natural laboratory where physics and chemistry manifest on a colossal scale, reminding us that there is still much to discover about these gaseous guardians and their influence on the balance of our cosmic neighborhood. What happens when a massive star reaches the end of its life? Many would think it simply disappears, but the reality is much more spectacular. When a star exhausts its nuclear fuel, gravity takes control and the star collapses in on itself in a violent process known as a supernova. This explosion is so powerful that for a few days or weeks, the star can shine brighter than an entire galaxy. But what remains after this cosmic outburst? The remnant of a supernova is, in essence, a stellar graveyard. However, far from being a silent and empty place, these remnants are cosmic laboratories where the heaviest elements in the universe are forged. Iron, gold, silver, and even the iodine that is part of our bodies are born in the heart of these explosions. It's curious to think that every atom of calcium in your bones was once part of a star that exploded millions of years ago. Thus, stellar graveyards are, in reality, the quarries of life and matter. But what do these graveyards look like? What remains after the supernova can take various forms. Whimsically shaped nebulae, composed of gas and dust that slowly expand through space, or even incredibly dense objects like neutron stars and black holes. Supernova nebulae, like the famous Crab Nebula, are true mosaics of colors and energies, charged with radiation and traversed by shockwaves, traveling at unimaginable speeds. In these places, matter is recycled and can give rise to new stars and planets. And why are these stellar remnants so important? Without them, the universe would be almost entirely made up of hydrogen and helium. Supernovas act as cosmic gardeners, seeding space with complex elements and enriching the gas clouds from which future generations of stars and planetary systems will be born. Thus, stellar graveyards not only mark the end of a star, but also herald the beginning of new cosmic stories, reminding us that, in the universe, every end is also a new beginning. If the universe is so vast, with hundreds of billions of galaxies and each containing trillions of stars, why haven't we found signs of intelligent life? This is the essence of the Fermi paradox, an enigma that has puzzled scientists and philosophers for decades. According to the most optimistic calculations, there should be hundreds, perhaps thousands of advanced civilizations just in our galaxy. However, the silence is absolute. There are no signals, no visits, no traces. Where is everyone? One possible answer is that intelligent life is extremely rare or very fleeting. The emergence of complex life may be such an improbable process that, even though the universe is enormous, it has only happened once in each distant corner. Or perhaps, when a civilization reaches a certain technological level, it self-destructs, whether through wars, climate changes, or failed experiments. Like a candle that burns too quickly, intelligent life may simply not last long enough to find each other. Another fascinating hypothesis is the so-called Great Filter. Is there an invisible barrier that almost no civilization manages to overcome. This filter could be in our past, perhaps the very origin of life, or the leap to conscious intelligence, or in our future, with technological or ethical challenges that are impossible to navigate. If the great filter lies ahead of us, humanity may still face an existential test that will define its fate. There is also the possibility that civilizations are out there, but they are so different from us that we don't know how to search for or recognize them. Perhaps they employ incomprehensible technologies, communicate in ways we cannot detect, or simply choose to remain silent, hidden for precaution. Like children trying to catch a conversation between adults through a wall, we could be surrounded by signals that we still do not know how to interpret. Thus, the Fermi paradox continues to raise unsettling questions. Are we the first, the only ones, or simply the loudest in a silent universe? What would happen if you got too close to a black hole? There is an invisible limit around these cosmic monsters called the event horizon. More than just a simple boundary, it is the point of no return, the place where gravity is so intense that nothing, not even light, can escape. Beyond that threshold, all information and matter are trapped forever, becoming part of the mystery that surrounds these extreme objects. But how is the event horizon really understood? Imagine standing at the edge of a gigantic waterfall. The closer you get to the edge, the harder it is to paddle against the current, until there comes a point where, no matter how hard you try, the current is so strong that you inevitably fall. Similarly, the event horizon marks the region where the curvature of space-time is so pronounced that no ship, signal, or particle can return to the outside universe. It's like a door that only opens in one direction, inward. Does everything that falls into a black hole disappear? According to general relativity, the information about the matter that crosses the event horizon is forever hidden from those observing from the outside. However, this has sparked one of the most heated debates in modern physics, the famous information loss problem. Is information really destroyed, or does it remain encoded in some yet unknown form? This enigma connects quantum physics with gravity, two fundamental pillars of human knowledge that still cannot be fully reconciled. The event horizon is not a solid physical surface, but a mathematical boundary, a region defined by the geometry of space and time. If an object or a person were to cross that limit, from their perspective, nothing extraordinary would happen at that precise moment. They would only notice in a brief span that the outside universe fades away and time seems to distort. For a distant observer, however, they would see the object slow down and slowly fade away, never actually crossing the horizon due to the extreme effects of time dilation. In this way, the event horizon represents one of the most fascinating and challenging phenomena of the cosmos, the place where known reality blurs and the realm of the unknown emerges. What makes Io, one of Jupiter's moons, so special in our solar system? At first glance, it might seem like just another satellite lost among the many that orbit the gas giants, but Io is, in fact, the most volcanic place known, a world where the surface is in constant transformation, dotted with hundreds of active volcanoes that shoot columns of sulfur and lava to heights exceeding 100 kilometers. How is it possible for such a dynamic hell to exist in such a distant corner of the solar system? The key lies in the gravitational dance between Io, Jupiter, and the other Galilean moons, Europa and Ganymede. These moons pull on Io as if they were invisible hands kneading a ball of clay. This constant stretching and compressing generates tremendous internal heat, enough to melt Io's interior and fuel its volcanoes. Unlike Earth, where volcanism is mainly due to the planet's residual heat and tectonic plate activity, Io is a natural laboratory for how gravity can sculpt a world from the inside out. Can you imagine being on the surface of Io? There, the ground is yellow, orange, and red due to deposits of sulfur and volcanic compounds, and the landscape changes with each eruption. Some volcanoes, like Loki Patera, are so large and active that their glow can be observed even from Earth-based telescopes. On Io, there are no seas, rivers, or dense atmosphere, just an endless cycle of destruction and creation, where new layers of lava cover the terrain, as if every day were the first. But why is it important to study such an inhospitable place? Observing Io helps us understand how gravitational energy can trigger geological activity on distant worlds, and it also gives us clues about what landscapes might be like on moons of other stellar systems. Io challenges the idea that only planets can be geologically active, and reminds us that, even in the most extreme corners of the cosmos, nature finds spectacular ways to surprise us. Did you know that the universe has its own magician's trick? There is a fascinating phenomenon that allows us to see objects that would otherwise be completely hidden behind other cosmic bodies. This trick is called gravitational lensing. But how is it possible for gravity to behave like a giant magnifying glass in space? It all goes back to Einstein's theory of relativity, which demonstrated that the mass of an object not only attracts other bodies, but also deforms space and time around it. Imagine space as an elastic sheet. If you place a heavy ball in the center, the sheet sinks. Now, if you throw a marble near the ball, its trajectory curves following the deformation. Thus, the light from a distant galaxy can bend and wrap around a closer galaxy, reaching us through unexpected paths. But what is the purpose of this phenomenon in astronomy? Gravitational lensing is a fundamental tool for studying the deep universe. It allows us to observe galaxies and stars that are so far away that their light could not reach us directly. When the light from these objects passes near a massive mass, like a galaxy cluster, gravity deforms and amplifies that light, creating distorted images, multiple reflections, and even colorful arcs in the sky. Thanks to this effect, astronomers have discovered some of the oldest and most distant galaxies, observing the past of the universe as if looking through a magical window. And what implications does this have for our understanding of the cosmos? Gravitational lensing not only reveals what is hidden, but also helps weigh the universe. By analyzing how light curves, scientists can estimate the amount of mass, both visible and invisible, present in a galaxy cluster. Thus, gravitational lensing has been key in demonstrating the existence of dark matter, that mysterious substance that does not emit light but whose gravity leaves traces in the fabric of space. Without this effect, much of the hidden side of the universe would remain an enigma. As if that weren't enough, gravitational lenses have also allowed us to measure the expansion of the universe and test the validity of the most advanced physical theories. Some events, like the perfect alignment between a distant galaxy, a massive intermediate galaxy, and Earth, can produce what is known as an Einstein ring, an almost perfect image of distorted light in the shape of a circle. Isn't it amazing to think that, thanks to gravity, the universe becomes its own optical laboratory, allowing us to look beyond the limits of direct observation? The gravitational lensing effect is undoubtedly one of the most elegant and useful phenomena in modern astrophysics. Is there something in the universe that we cannot see, touch, or directly detect, yet still dominates most of its mass? Such is dark matter, the greatest invisible enigma of the cosmos. Although its name suggests something exotic, it actually refers to a substance that neither emits, absorbs, nor reflects light, making it undetectable by our traditional telescopes. But if we cannot observe it, how do we know it's there? The answer lies in the movement of stars and galaxies. If we were to look at a spiral galaxy, we would notice that its stars rotate so quickly that, according to known laws of physics, they should be flung out into space. However, they remain bound together, as if an invisible force is keeping them tied. It's like watching a Ferris wheel spin at full speed without its cabins breaking off, thanks to hidden cables we cannot see. That extra gravity is attributed to dark matter, which acts like cosmic glue holding galactic structures together. Over the past few decades, scientists have devised increasingly sophisticated experiments to try to uncover what dark matter is made of. They have concluded that it is not hidden planets or clouds of dust, but something much stranger, still unknown particles that interact very weakly with ordinary matter. Could dark matter be composed of exotic particles like axions or WIMPs? So far, all searches have been fruitless, deepening the mystery. Beyond holding galaxies together, dark matter has played a fundamental role in the formation of the universe as we know it. Without it, normal matter would not have had enough gravity to clump together and form stars, planets, and galaxies. It's as if the universe needs this invisible structure to build everything visible. Despite all scientific advancements, dark matter remains one of the greatest challenges of modern physics, an essential piece of the cosmos that, although we cannot see, we know is there, challenging our understanding and fueling human curiosity. How do we really know that the universe is expanding? This question has intrigued scientists for generations, and the answer revolves around the so-called Hubble constant. This value, far from being just a number, is the key that allows us to measure the speed at which galaxies are moving away from each other, as if they were all mounted on a gigantic cosmic conveyor belt that stretches endlessly. But how did we come to discover that the universe is not static, but dynamic and constantly growing? The story begins in the 1920s when Edwin Hubble observed that the farther away a galaxy was, the faster it seemed to be moving away from us. What was behind this phenomenon? The explanation lies in the redshift of light, an effect similar to the sound of an ambulance siren changing pitch as it moves away. In the case of light, when a galaxy moves away, its waves stretch and shift toward the red end of the spectrum. Thus, Hubble deduced that the entire universe is expanding and formulated a simple mathematical relationship. The recession velocity of a galaxy is proportional to its distance, and the Hubble constant is that factor of proportionality. However, is the Hubble constant really constant? This question has sparked debate and controversy in the scientific community. There are two main methods to measure it. One uses observations of the early universe, analyzing the cosmic microwave background radiation, and the other studies the light from nearby stars and galaxies. Interestingly, the results do not match exactly. The early universe method suggests a slightly lower value, while the local method indicates a faster expansion. This mystery, known as the Hubble tension, has led some astronomers to wonder if we are facing new laws of physics or if there is some detail that still eludes us. And why is it so important to know the Hubble constant accurately? Because our understanding of the age, size, and ultimate fate of the cosmos depends on it. If the universe is expanding faster than we think, it is younger, and its future could be very different from what we imagine. If it is expanding more slowly, it is older, and its fate could be another. Thus, measuring the Hubble constant is not just a mathematical exercise. It is an attempt to decipher the past and future of the universe, and an invitation to continue exploring its deepest secrets. Is it possible that there are planets literally made of diamond? Although it sounds like science fiction or a jeweler's fantasy, modern astronomy suggests that these exotic worlds are more than mere speculation. It all begins with carbon, one of the most abundant elements in the universe, and the extreme conditions that can only be found beyond our solar system. But how could a planet form with a heart of diamond? The secret lies in carbon-rich stars and their cosmic legacy. When one of these stars ends its life, it can leave behind remnants with a chemical composition very different from that of our own solar system. If a planet forms in a region where carbon exceeds oxygen, the conditions may favor the crystallization of enormous amounts of pure carbon under colossal pressures and temperatures. The result, a core or even entire layers of diamond that envelop these alien worlds. We're not talking about small diamonds, but structures so large that any terrestrial mind would seem insignificant. One of the most famous candidates is the planet known as 55 Cancri E. This world, twice the size of Earth and located about 40 light-years away, has fascinated astronomers since its discovery. Analyses suggest that up to a third of its mass could be composed of diamond and other crystallized carbons. Now, what would it be like to be on the surface of such a planet? Probably nothing like a shining paradise. The extremely high temperatures, exceeding 2000 degrees Celsius, and the crushing pressure would make any form of life we know impossible. These planets not only spark the imagination for their material value, but also for what they teach us about the diversity of the cosmos. What other exotic materials could form worlds in other solar systems? The study of diamond planets reminds us that our Earth, with its familiar mix of rocks and water, is just one possibility among many. In the universe, the chemistry of planets can be as varied as it is surprising, and we are still far from knowing all the treasures that the sky holds. What if the universe, instead of being completely uniform and chaotic, had a kind of preferred direction, a mysterious alignment that defies our expectations? Scientists have found something unsettling while investigating the cosmic microwave background radiation, that luminous echo of the Big Bang that fills all of space. By precisely analyzing the distribution of this radiation, an anomaly emerged. Certain fluctuations seem to align along a specific axis, an unexpected orientation that has provocatively been named the axis of evil. Why such a dramatic name? Because this axis seems to defy one of the fundamental principles of cosmology, isotropy, that is, the idea that the universe is the same in all directions. If the cosmos were like a perfectly mixed soup, there would be no reason for a special direction to exist. However, data from the WMAP satellite and later from the Planck telescope revealed that the largest scales of the background radiation exhibit this strange alignment, as if there were an invisible seam in the universal tapestry. Could it be a simple error, an artifact of our instruments, or the way we interpret the data? Many astronomers have tried to find mundane explanations, such as interference from the Milky Way or flaws in signal processing. However, after multiple reviews and independent teams, the anomaly persists, even though its meaning remains an enigma. Some theorists have suggested that it could be a clue about unknown phenomena from the early universe, or even a signal that the cosmos is stranger than we imagine. The existence of the axis of evil forces us to ask fundamental questions. Is it just a statistical coincidence, or are we facing the imprint of yet undiscovered physical laws? If this axis truly exists, it could imply that the universe has a large-scale structure much more complex than current models predict. For now, the axis of evil remains a cosmic provocation, reminding us that, although we believe we understand the universe, there are always hidden mysteries waiting to be revealed. In the vast stage of the universe, galaxies are not static or solitary entities. Contrary to what we might think, many of them live in constant interaction and, at times, star in one of the most dramatic phenomena of the cosmos, galactic cannibalism. How is it possible for one galaxy to devour another? The answer lies in gravity, that invisible force that acts like a cosmic choreography, bringing together, deforming, and ultimately merging stellar colossi. When two galaxies approach closely enough, the more massive one exerts such intense gravitational attraction that it begins to tear apart its smaller companion. The stars, gas, and dust of the victim galaxy are ripped away and absorbed, adding to the disk and halo of the dominant galaxy. This process can last hundreds of millions of years and usually does not involve direct collisions between stars, as, incredible as it may seem, the distances between them are so vast that the probability of a collision is minimal. The final result is a single galaxy, larger and more complex, enriched with the material of its former rival. Did you know that our own galaxy, the Milky Way, is a veteran in this type of encounter? Throughout its history, it has absorbed several dwarf galaxies, and in fact, at this very moment, it is in the process of devouring the Sagittarius dwarf galaxy. The traces of these cosmic banquets can be observed in the form of stellar streams, like ghostly trails that traverse the galactic halo. These streams are the scattered remnants of the devoured galaxies, and their study allows us to reconstruct the merger history of the Milky Way. This cannibalism is not exclusive to our galaxy. In galaxy clusters, the larger galaxies, known as giant elliptical galaxies, have grown by feeding on their smaller neighbors. This dynamic has shaped the universe as we know it, and each merger has a profound impact. It can trigger bursts of star formation, alter galactic morphology, and sometimes awaken the supermassive black holes that reside in the cores of galaxies. Thus, in the universe, survival and growth often depend on the ability to devour and assimilate others. Who will be the next victim in this endless banquet? Is it possible for time to pass at different speeds, depending on where you are or how fast you move? Although it sounds like science fiction, this is a reality demonstrated by Albert Einstein's theory of relativity. Time dilation is one of the most fascinating phenomena in the universe. Time, far from being absolute and universal, is flexible and depends on the physical conditions in which it is measured. But what does it really mean for time to dilate? To understand it, let's think of two perfectly synchronized clocks. One remains on the surface of the Earth, while the other is sent into space on a ship traveling at a speed close to that of light. When they meet again, the clocks will show different times. The clock that was traveling will have advanced more slowly compared to the one that stayed on Earth. Why does this happen? Because at extreme speeds, time stretches for the traveler, an effect proven in experiments with subatomic particles and even in the clocks of GPS satellites, which require constant corrections to stay synchronized with the clocks on the Earth's surface. Not only speed causes time to dilate, gravity also plays a crucial role. The closer you are to a massive object, like a planet or a star, the slower time will pass for you compared to someone who is farther away. This phenomenon is known as gravitational time dilation. For example, if you could spend a day near the event horizon of a black hole and then return, you would find that many years may have passed on Earth. It's as if the universe has different clocks depending on the presence of gigantic masses or how fast you are moving. Does this mean that one day we could travel to the future simply by getting close to a source of extreme gravity or traveling very fast? In theory, yes. Time dilation is one of the few ways that physics realistically allows for time travel into the future. However, the technological challenges are enormous, and the experience would be very different from how we imagine it in movies. The most fascinating thing is that at both microscopic and macroscopic levels, this flexibility of time is an integral part of how the cosmos operates. The next time you look at a clock, remember, the time it measures is just one of the many possible versions that exist in this relative universe. What do such distinct cultures as Greek, Japanese, and Aztec have in common? They have all observed and told stories about the same group of stars, the Pleiades. Also known as the Seven Sisters, these stars make up the most famous and recognizable open cluster in the night sky. But why do they evoke such fascination? Since ancient times, their appearance marked the beginning of agricultural cycles, festivities, and rituals in civilizations around the world, demonstrating that the sky has always been humanity's great calendar. The Pleiades are located about 440 light-years from Earth, in the constellation Taurus. Although 6 or 7 stars can be distinguished with the naked eye, the cluster actually consists of over 1,000 members. The reason we only see a few is that most are too faint for our eyes, but with binoculars or a simple telescope, the spectacle multiplies. Did you know that the main Pleiades are young stars, only about 100 million years old, and much hotter and brighter than our own Sun? What makes this cluster so special from a scientific point of view? The Pleiades are a natural laboratory for understanding how stars are born and evolve. They are enveloped in a faint bluish nebula, a trail of interstellar dust that reflects the light of the young stars, like dust highlighting the beams of a flashlight in a dark room. Studying this cluster helps astronomers calculate distances in the universe and refine stellar formation models, because all its stars formed more or less at the same time and from the same material. But why the number 7? It's a question that has intrigued generations. Although the human eye usually distinguishes only 6 stars, the myth of the 7 sisters appears in dozens of cultures. Some suggest that in the past the 7th star was brighter, or that the legend arose from humanity's tendency to find patterns and give them meaning. Beyond the exact number, the Pleiades are a bridge between science and mythology, reminding us that looking at the sky has always been, and continues to be, an act of wonder and discovery. What would happen if a moon gets too close to its planet? Is there an invisible point in space where gravity becomes a destructive force? That critical point exists and is called the Roche limit. This concept, although it sounds like science fiction, is key to understanding why some celestial bodies remain intact while others end up in pieces. The Roche limit is the minimum distance at which a satellite can orbit a planet without being disintegrated by tidal forces, those same forces responsible for the tides on Earth, but taken to the extreme. Imagine it as a tug-of-war of gravitational pulls. If a moon ventures too close to its planet, the planet's gravity pulls so strongly on the moon's nearest side compared to the far side that it literally starts to tear it apart. It's like trying to stretch a piece of modeling clay with both hands. If the force is strong enough, the clay breaks. In space, this process can turn a solid moon into a ring of debris orbiting its former planet. Did you know that Saturn's stunning rings are a direct result of this phenomenon? It is believed that, at some point in the past, a moon crossed Saturn's Roche limit and was shattered, scattering its remains into orbit. That's why the rings are nothing more than a graveyard of fragments that could never come together to form a moon. This rule also explains why the rings of giant planets never become satellites. The tidal forces within the Roche limit prevent the fragments from reuniting due to destructive gravity. The Roche limit not only determines the fate of moons and rings, but it also marks a natural boundary for the stability of planetary systems. If an object, like a comet or an asteroid, ventures too close to a massive planet, it can be crushed and dispersed. This principle even applies beyond the solar system. In exoplanets with moons and rings that obey the same fundamental rules. Thus, the Roche limit serves as a reminder that, in the universe, attraction can be as dangerous as it is irresistible. Did you know that in our solar system there are asteroids that, instead of following independent trajectories, share their orbit with giant planets like Jupiter? These bodies are known as Trojan asteroids, and they are true masters of cosmic camouflage. Their peculiarity lies in the fact that they do not orbit randomly in front of or behind the planet, but rather cluster at 2 very special points, the so-called Lagrange points L4 and L5, which are located approximately 60 degrees ahead and behind the planet in its path around the Sun. It's as if they are invisible travel companions, hidden in the gravitational folds of space. What makes these points so attractive to asteroids? The answer lies in the delicate balance of forces between the Sun, the planet, and the asteroid itself. At the Lagrange points, the gravity of the planet and that of the Sun combine in such a way that they allow an object to remain there stably for millions of years. It's the astronomical equivalent of finding the exact point on a roller coaster where you can float without moving either forward or backward. This phenomenon does not only occur with Jupiter. There are also Trojans in the orbits of Mars, Neptune, and even a small population in Earth's orbit. The term Trojan has its origins in Greek mythology, because the first asteroids of this type were named after the heroes of the Trojan War. In the case of Jupiter, for example, the Trojans at the L4 point usually bear names of Greeks, while those at the L5 point are named after Trojans. But beyond the nomenclature, what is fascinating is that these asteroids form true swarms, with hundreds of thousands of members just in Jupiter's orbit. Some scientists believe they could be primitive remnants of the material from which the planets formed, genuine time capsules that hold secrets about the origins of the solar system. Could these Trojans hide any surprises? Some theories suggest that they might contain organic compounds or even water, making them very interesting targets for future space missions. Additionally, studying them helps to understand the dynamics of planetary orbits and the history of the great migratory movements of planets in the early solar system. In summary, Trojan asteroids are the silent and discreet guardians of orbital paths, reminding us that even in the most hidden places of the cosmos, there are stories waiting to be discovered. What does the universe tell us about ourselves? By observing the stars, planets, and the strangest phenomena of the cosmos, we not only discover the nature of these distant objects, but also learn about our own existence. Have you ever stopped to think that every atom in your body was once forged in the heart of a star that exploded billions of years ago? We are, literally, stardust contemplating the origin and destiny of everything. But why is the universe so diverse and yet so mysterious? From planets where it rains diamonds to colossal structures that defy our imagination, the cosmos seems filled with unanswered questions. What lies beyond the observable horizon? Are there other forms of life waiting to be discovered? Or are we alone in this vast darkness? Each finding, far from closing doors, opens new windows to human wonder and curiosity. Many might wonder if we will ever understand it all. Science, like a flashlight in the dark, allows us to see a little further, but shadows always remain in the corners. What is the dark matter that holds galaxies together? What is the ultimate fate of stars and the universe itself? These mysteries drive us to keep exploring, to create new theories, and to challenge our limits time and again. Thus, the universe is like an infinite book whose pages are written with each new observation and each bold question. The wonder lies in not knowing everything, in the possibility of discovering something that changes the course of human history. When we look to the sky, we not only seek answers, but also reaffirm our ability to dream and imagine the impossible. What will the next great discovery be? Only time and our insatiable curiosity will tell.